that square bracket that I said means, hi, I'm a lambda? It's actually called the capture clause. The empty ones, like you've seen so far, means that the lambda doesn't capture anything, doesn't have any extra member variables in the anonymous function object that's generated for it. It works only with parameters passed into the function, the integer n, of which element of the vector are we going through, for example. That's not the only way to write a lambda. If I put in those square brackets x comma y, it means that I'm capturing x and y from the scope that's local at the moment where I created the lambda to actually be saved into the lambda's object. And later, which might just be, we're passing it, but you can put it in a variable, a member variable, and it can have a really long lifetime. Later, when the lambda is executed, those member variables will be used. Because I'm capturing by value, there'll be copies. The original x and y could have long gone out of scope. The copies are what will be used inside the lambda when it executes. If I want, I can capture x and y by reference. So you can imagine that the member variables are now integer references instead of integers if x and y happen to be integers. We're not making copies. If I make a change to x and y in the lambda, that change will be reflected in the original calling scope that those values came from. And of course, if the original calling scope has gone away and x and y aren't there to refer to anymore, then you have a dangling reference problem, the same as you would if you just stored the reference somewhere and then tried to use it after the original guys had gone out of scope. Couple of shortcuts. If I type an equal sign inside that square bracket, we generally pronounce that as saying, oh, we're capturing everything or we're capturing the whole stack. To be fair, the code that generates the anonymous function object for you actually goes through and looks and sees what you need. So if you access 3 things from local scope in the body of the lambda, there'll be 3 member variables corresponding to those 3 things. There may be 10 or 15 other variables in local scope that won't get added as member variables into your anonymous function object. Similarly, I can capture so-called everything by reference, again, only the things that are actually used in the body of the lambda. And you can mix and match, capturing x by value and everything else by reference, for example. I mentioned that these member variables were const by default. If you want to change them, you have to use the keyword mutable, which indicates that you're going to be writing code inside the body of the lambda that changes something that it's captured from local scope. If it's captured it by value, it will change the local copies and have no impact on the calling scope. If it's captured it by reference, it will change the real things to which they refer. Some capture examples. Here, I've set up a couple of local variables in my calling scope, x and y, and put some values into them. Then I have the same kind of for eaching that we've been doing all along, and my lambda, the third parameter to that for each call, this time is capturing x and y in the square brackets. So you see it using x here and using y here. And all I'm going to do is print out only elements of the vector that are, in this case, x is 3, so 3 or more, and simultaneously they are 7 or less. So we'd expect to see 3, 4, 5, 6, 7. Then I'm going to print the vector out just to prove that it hasn't been changed. So this app is still running. I'm going to run down to here and show you the output. You see 3, 4, 5, 6, 7 down here, and the vector itself still unchanged. This lambda captured this x and y from local scope. It's not really running here when they are in scope. It's using its own copies that are in the member variables of the anonymous function object. It just feels exactly like still these being in scope and still using them. I can do the same thing. I've just changed the values of x and y to make it obvious, capturing, quote, everything, unquote, Now, it really doesn't capture everything. There's an awful lot of things that are in scope at this point in this application. We've got our vector v, we've got our second vector v2, we've got a vector of doubles called dv, and a whole pile of other things that I've sort of created as I went along throughout the various demos of this module. Only x and y will actually be captured by that equals sign. This is the exact same code, but with 2 and 9 instead of 3 and 7. So if we run down to here, you can see that we're printing out 2 through 9 and that the vector is still unchanged. What if I wanted to change x or y or elements of the vector that I'm iterating over? A couple things going on here. First of all, I'm capturing, quote, the whole stack again by value. So that's x and y because they're used here. But I've put the word mutable in the declaration of the lambda. That's what enables these lines to compile. Normally, x and y would be const member variables of the lambda's anonymous function object. But because of the word mutable, I'm allowed to change their values. However, because I'm capturing them by value, as you see here, when I print it out here, x and y, you'll see that in fact they are still unchanged. So I changed them both a lot as we went through, old being the element of the vector. So the first time through, old's going to be 0, and x will become y, which is 1, and y will become 0. But as we continue to go through, and the last time we go through, old will be 9, the last element of the vector, and y would become 9, and x would be 8 from the time before. However, when I run this, you'll see that in fact x and y are still going to print out as 1 and 1 because the lambda is only changing its own local copies of x and y. I've also changed the parameter to the lambda from an integer, which it's been in all the other examples, to an integer reference. And that means that here, when I change r, I'm actually changing the real values back in that vector v. So we're going to print out that vector v so that you can see that that's what's happened. So run down to here, take a look at the output. The vector has actually doubled, but x and y are still 1 and 1. If I want to capture x and y by reference, so here I'm going to clear my vector, that's a vector method that I've mentioned before without showing, and then push 0 through 9 back onto it again. So we've gone from the 0, 2, 4, 6 back to the 0, 1, 2. This is the exact same body of the lambda, but the capture clause is different. I'm capturing x and y by reference. That way, as we go through, old taking on the value of the value we're on the vector, x being y, y being old, we'll end up with 8 and 9, as well as continuing to double the elements of the vector, which we're taking by reference. So we're really doubling the real vector elements. So when we come here, you see that x and y are now 8 and 9, as well as doubling the vector. It's totally up to you as the C++ developer what you capture by value, what you capture by reference, whether you take your parameters by value as we're doing here when we're just printing them out, or by reference as we're doing here when we actually want to change them. Just so that you can see one that takes the quote whole stack by reference, this is another way to fill the vector. I clear it, and then I use a standard function called generate n. Generate n takes a particular transformation function like back inserter, which we were using in transform, and says do it, in this case, 10 times. And what is it that I'm going to do? Well, I'm using a lambda. And I'm simply working with this I and incrementing it. And because I've captured that I by reference when I'm incrementing it, I'm incrementing the real I. So when we come out the other end, for example, you'll see that I ends up being 10, having gone through 0 through 9. So if I run down to here, there is my vector one more time, initialized a slightly different way, and there is my I that got incremented up to 10 after running through the back inserter 10 times. Now you've seen how C++ takes such tremendously fine-grained control over the capture of the lambda. This really sets it apart from some other languages that don't give you this level of control. So everything you can do with a lambda, you could have done with a more complex structure in the past. You could have written an anonymous function object yourself and passed it as the third parameter to a library for each call. Or you could have written a little function like print and odd in the previous module and used them in that function call to for each or find if or what have you. But using lambdas right there increases the readability of your code tremendously and the maintainability. For me, it's the difference between being willing to use those standard library functions and not being willing to use those standard library functions. When I use a language for, I can see what happens in the loop right there. When I use a for each without lambdas, I have to write a different function which is perhaps thousands of miles away, and I can no longer see what's happening for each loop of the for. Using a lambda instead brings me back to parity with the language for. I can see exactly what's happening on each iteration through the whatever it is I'm for eaching through. That alone carries great value. But on top of that, a number of developers have chosen to ship libraries that bring cool functionality to C++ developers, sticking to the paradigm of the for each. Just two examples, there are dozens more available. Parallel for eaches on the CPU and on the GPU in separate libraries that take the exact same parameters as the standard for each, so that you literally just edit your for each to a parallel for each, maybe change one or two parameters, you're done. You are now parallelized across the CPU or leveraging the power of your video card across the GPU. Really easy to do because you've accepted I'm going to use the standard for each rather than the language for. This really affects the way you think, affects the way you write code, affects the way you read code. To my mind, as I've said before, it is the most important C++ 11 change because of so much else that it enables. Now, of course, this being C++, C++ lambdas can't be just like everybody else's lambdas. We're the language of power and control and performance, and so C++ lambdas lets you specify whether you're capturing by value or by reference. And they do that so you can have power and control and performance, because that's always what C++ is all about.